My name is Cleber Rosa. I'm a software engineer at Red Hat. I work at the virtualization team, mostly on testing-related initiatives. Most specifically, most of the time, on a couple of projects that are really focused on testing and virtualization testing as well, which is Avocado and Avocado-VT. Today, we're going to be talking about basic software practices. So it's going to be a little bit of basic software testing theory. We're going to move into topics which are simple but have kind of fancy names. So we're going to try to demystify them. These are equivalence partitioning, boundary value analysis, and we're going to move into a possibly more interesting topic that will build on those, which is called combinatorial testing. And we're going to always be looking at how we can apply those techniques and a few tools on virtualization testing. So as promised, we're going to start with the textbook example. Most software testing books, they either mention or they incorporate one example which comes from Glenford J. Myers, which presents the following situation. Suppose you're writing an application that's pretty simple. You just have to take as input the 3 lengths of a triangle situs, and you have to output the triangle classification. The point is, how hard can it actually be to write such tests? So we'll start with a very basic, actually rather naive version of the code that actually does that. And it just checks if the 3 sizes are the same, it returns equilateral. If the sizes are different, it's a scalene triangle, and in the last situation where the two sizes should be the same and the other one different, it returns isosceles. So we, applying the methodology on software testing textbook, we just come up with the 3 test cases, like 3 really basic test cases. These are all sizes are equal, it's equilateral, 2 equal and 1 different, isosceles. And finally, the last one is scalene. So we just do kind of a direct translation of that into tests. People familiar with unit tests should be able to read this pretty quickly. So it's just like a direct translation of that code. But in fact, there are situations in which our naive code, even with very simple extended test case, can actually reveal problems. So if we look at the original code, so this is the implementation together with the test. If we run something like this, so I'm using the Avocado test runner for that, we have all passes, but if we expand this with something that initially we think should also be an isosceles triangle, we are going to see that there's a failure. So it actually reveals a bug right away just by picking the right input value. So we go ahead and add an extended test, we catch errors, but we are pretty much far from comprehensive test coverage in such a simple program. So we can think about situations where we have a size of the triangle with null size, so it's 0 length size. The expected outcome for that is an error. Negative sizes are also an error. And there are also situations where you would expect something to be an isosceles triangle, but they are not, and also a scalene triangle, but they are not. So one of those situations we can translate as code like this. So again, pretty much simple code. And the other situation where you expect triangles to be scalene or isosceles and they are not, are based on the fact that the sum of 2 sizes of a triangle has to be larger than the other one. And we can take from there and add yet a whole next level of checks. So permutations of the parameter orders are actually important and can impact the code that we have. The type of input that your program actually gets can actually lead to revealing problems. And even the amount, like the number of parameters that your program gets, can quickly show you problems. So after 5 rounds of changes to the code and actually new tests, we come up with a much more lengthy version of triangle check that checks inputs, checks negative numbers, checks all combinations of the orders of the parameters, and check the sum of two sizes against the third one. And finally, a different implementation that actually checks the number of unique sizes. And out of this, we have 9 test cases. So I've said all that because the lessons that we can learn from this simple example is that writing tests, it's probably a little bit more, it takes a little more energy than one would expect. So even experienced software developers, like using the textbook example, they can come up with about 6 or 7 tests for this simple situation, and one would expect at least 14 tests to cover all corner cases. The point is, we are probably writing software that is not as simple as a triangle check, right? So we have to do at least a number of orders of magnitude better than the test that I've shown here. One point that I'll try to get across this talk is that choosing the right input can actually help a lot. So we'll be focusing on spending our energy and where we can reap the most benefits out of testing. So the idea is that not all input are created equal, and we can actually exercise the best input that we pass. So the first technique that we're gonna talk about is equivalence partitioning. Is anyone here familiar with that, with the term? If not, don't let the name scare you. It's actually something pretty simple. It's actually built into our logical thinking. It just makes sense to actually name it and have a technique for finding, for identifying and making use of that. So when you actually write an application and consequently a test, you can think of values in which you pass through the test, which you can reasonably expect that will produce the same kind of result. So these types of input would be in the same class. And a good pick is one that is usually worth many others. So if you're checking number 1 as a given input to a function, and you're reasonably sure that if you pass 2 instead, 1 and 2 would be in the same class. There's no need to test with 1 and 2. You reasonably expect them to behave the same. So in virtualization development, we're usually bound to following real-world hardware. So we would be following like specifications of real hardware, or when we're writing tests for say QEMU, we should be looking at the limits in which this virtualized hardware actually imposes. So this is a snippet from QEMU source code in which it presents 2 kinds of limits. The first one, it regards the maximum ID of a CPU hot plug, which gives away also the second check, which is the maximum number of CPUs that can be added to a virtual machine. So by looking at this code, we can identify 2 types of inputs in their respective classes. So when it comes to the number of CPUs, we can quickly see that the QEMU source code should treat from 1 to 256 CPUs kind of the same way. That's what expected, so we can reasonably assume that. But anything equal or below 0 would be an invalid input, and anything above 257 would be invalid. These 2 are closely related, but we really have to look at them differently. So if we look at the IDs that each CPU will actually have, it's a different input type, and they have a different class of input. So anything from 0 to 255, they should be valid inputs for CPU IDs, and anything below or above that should be invalid. So whenever you hear equivalent classes or equivalent partitioning, that's all it is. So you're putting in the first example, from 1 to 256 in the same class, and anything above it and beyond it on separate classes. And the same thing for other types of input. The next topic, it's also pretty simple, even though it has this fancy name, boundary analysis. It's just a way of looking at the values that are at the boundary of classes. They usually will give you the best benefits, the best results out of testing. So looking back at the equivalent classes we saw before, we can say that 0 is an invalid number of CPU IDs, and it just happens that it's really at the boundary of the valid and invalid class. And the same thing is, it's true for 257. So valid values and invalid values can be used as input for tests that test correct behavior and also test error handling. That should be pretty simple, right? The same thing with CPU IDs in this case. So we have here an invalid CPU ID that is -1, and an also invalid CPU ID of 256. So boundary values, it's only this. Like, you look at the boundary values in equivalent classes, and you can usually get a lot just by using those values. So just to prove that sometimes this come up consciously and sometimes unconsciously, this is a snippet from Avocado-VT TP QEMU. So it's the test provider, the set of tests for QEMU that is also part of the Avocado project. And it may be coincidence, it may be not. I wasn't there when the code was written, so I don't know what was in the developer's mind. But you can pretty much see that the boundary values are being used here. So it shouldn't come up as a surprise that these values are kind of special. So let's try to get this concept and actually apply to any piece of software. So it was literally the first thing that came to my mind when I was preparing this, is just to get this, like, one of the most easily, the components that was easier to interact with in QEMU, which was qemu-img. So I was looking at the commands, and I saw bench, and I read, run a simple sequential I/O benchmarks on the specified image. That's the description in the main page. And then the first option for qemu-img is a total number of count I/O requests, which is a parameter. Request is performed. So this comes from qemu-img. If we look at bench, it's the first parameter. So if we look based on this description, we could try something like this. So I'm going to do first to benchmark on a qemu-img image. I'm going to create one. I'm going to create using raw. I'm going to name it bench-img, and I'm going to create it with 1 gig. So that's nice. We have an image, and now I'm going to try bench. The first parameter is count. I don't need the image size. And I'm going to try to send a negative number of requests. In my mind, this doesn't make sense. And it doesn't make sense to qemu-img as well. So this is a boundary value. If I had previously drawn that, it would be pretty obvious. But now I'll go a little bit further on the next boundary level and use 0. What happens here is that qemu-img runs, and it sends 0 requests. In my mind, it doesn't make much sense to do a benchmark with no requests. So it is something pretty trivial. So it's not like this huge deal breaker. There's going to be a CVE and the word's gonna scream. It's really far from that, but it just shows that a little bit of reasoning on values that should or should not be accepted can do a big deal of difference in testing. So the benefits you can reap out are like pretty quick. So out of this experiment, I actually was looking at QEMU, and to me, again, this is the perceived values that I believe would be valid and invalid here. would be more or less like this. So 0 requests, in my mind, would be something to be considered invalid. And anything from 1 to an unsigned integer instead of an signed integer would be a valid number of requests. So if we look at the source code, this is actually a diff from actual to perceived. So in my mind, we should be really using here an unsigned int instead of a signed int, because it doesn't make sense to use either 0 or negative number of IO requests. So again, no big deal, but like it makes you think about the inputs that you're gonna pass to tests. And why is that so important? Because humans do that the best. Like humans can reason on really on the details of the software that we are testing. So let us humans do what we do best, and let machines do what they do best. And this is where combinatorial testing comes in. So this thing is also known as pairwise, so you may hear about it using that term. And the basic principle is that you will have in your test case, so your collection of tests, at least a single test that will use a pair of unique values. So the idea is that if you have a matrix of tests, you would have a unique value of each possible, each type with a unique value, but it would generate this like full-blown matrix that it would take a lot of effort to run. And pairwise, it's a technique where you will only put 2 unique values by default on your test plan execution. It will combine those in an optimal way. So the point here is that if you have a lot of knobs to turn and a lot of knobs to test, it becomes impractical like really quickly. So the average piece of software will have dozens, hundreds, sometimes thousands of different configurations. And testing all of them means like multiplying everything. To a developer working on a piece of software, that is impractical for both coding, like code writing reasons, and also for test execution times. So what this combinatorial testing, like what has research on combinatorial testing actually delivered? So this is part of a research from NIST, part of the US government, and they have found that when you jump from one single value in a test to 2, you have this huge improvement of failures that you catch in software. When you move to 3, 4, 5, and 6, you virtually catch all the software failures that you would with a full-blown matrix. So this usually means, it can mean running 100 tests or 300 tests instead of 10,000 and still achieving the same results. So it makes a lot of sense in virtualization testing because we do deal with a lot of different knobs, like different hardware, different cache sizes, different block sizes, all the different knobs we can turn in the software that we develop. So again, getting back to qemu-img, but using convert, which is a different qemu-img command, we can look at the number of knobs this specific command has. So we can list maybe 10, 12 different commands, and that is without going too deep into options like object image ops, which are can be actually much more complex than that. So to look at combinatorial testing, we'll start simple. We'll start with 4 knobs. So we will look into a test that actually converts from one format to the other using one type of source cache and another type of destination cache. So out of all those options, we're only going to pick 4, and we're going to see what it does. So how would I go about testing this, which would mean almost 3,900 tests if I explode the matrix? I'll show you that later, into a much more usable and runnable set of tests. So to do that, we have to pick a tool, and the tool we're going to pick is pict. So it sounds like a tongue twister, but the name of the tool is pict, as in pairwise independent combinatorial testing. This is quoted from their documentation. So pict generates test cases and test configuration. With pict, you can generate tests that are more effectively than manually generated tests and in a fraction of time. So this is what we want. We want to really reap out the benefits without spending too much energy. So let the machines do what they do best. This application is hosted on GitHub. It's part of a Microsoft effort, and it's licensed an MIT license. So following the usage guidelines or the input types accepted by pict, we come up with a tool with a file like this. So out of the 4 knobs where you can see on the last 4 lines, we say that we're going to pass different values to the format, output format, source cache, and cache knobs, so different types of input. And each one of them can accept those different values. So different image format types and cache types. And to convert an image, we actually need to create an image. So we are going to do that with different image size. 2 bytes, like trying to get as small as possible, and then just gradually growing to see if they have any different effects. Another interesting, other interesting values that we could try to apply here, and if you try to do that, you're going to find interesting things about QEMU-img, would be things like 8 exabytes, 8 exabytes plus 1, which will go beyond the boundary of the acceptable, in theory, input size. So let's see how we can use this file. So let's see qemu-img convert.pict. So this is just like a mirror of the command line options. A few things we ran into while checking out those values. So I chose input value as 2 bytes, 1 meg, 1 gig, and those format files. So by using the pict tool by itself and just passing the parameter file, this is what we get. So for input size, format, output format, source cache, and cache, our test plan, like our whole test case, will have 81 different tests. Each one of those lines, it would be a test in our test case, and we can be sure that any combination you mention of source format, destination format, source cache type, and destination cache type, is listed at least once in this test case. If we want to get more comprehensive, like we showed previously in the graph, so this is at order 2, so we already have a big jump from from a single parameter to a combination of unique values. If we want to go to 3, 4, 5, which is the limit of the number of the unique input types that we have, we can go all the way to 300. Let it run, but the number is something like 3,800 and something different test cases. If we go a little bit back on the number of unique values, like if we go to 3, we still have a lot less test cases, but based on research, we'll have pretty good coverage, right? So how can we leverage this definition of combinatorial testing? So we have this combination that can be generated by pict, but we need some machinery to actually pass those parameters to a test. And we need a test runner for that. And for obvious reasons, we're going to pick Avocado. Avocado is, in our opinion, a versatile test runner. It has a long time history and heritage in virtualization testing. So it came from what was known as KVM Autotest, then Virt test, and it has this close relationship with Avocado-VT. It has built-in supports for what we call test variants. In test variants, you write your test once, and it gets run a number of times with different parameters. So you probably can see how those things would fit. For more information, there's a bunch of pointers, but the important thing here is that we are using a proof of concept implementation that was done with pict. So let's see how a test using those things would look like. So this is like an Avocado instrumented test, so it's just a Python file that uses some specific APIs. On the setup method, we get some parameters and we just execute qemu-img create. On the test itself, what we do is we get those parameters, so output format, input format, the kind of cache. This is an optional treatment of compression or no compression. I'll show you guys that later. And then you just execute qemu-img convert. If the process executes correctly, we have a pass. If we have a process command error, we have a test failure. Okay? So if we just run this, it's going to use defaults. The defaults are hard-coded in there. But then we have, again, a proof of concept integration with pict. So we pass pict parameter file, qemu-img converter, pict, and the same test code will actually run for a number of different variations. And now getting back, so we have 81 different test combinations, so converting a file using qemu-img from one format to the other with different sizes, just writing a single test. And what's interesting here is that if we apply what we have learned before on boundary values, so if I just substitute this 2 bytes for a 0-byte file, we're going to find out that for one specific combination, which is VMDK, we have a strange situation. If we look at the logs that are generated here, so I'll just go really quickly here to the log, and it says the command qemu-img create VMDK, a name of an image file, has failed, 0 bytes. And let's look at what this looks in real life. So I'll just substitute the file name because this is a directory that does not exist out of the test runtime. And we have a pretty much interesting message. So formatting image and then could not open input.img. So definitely something to look into. Maybe not a CVE, maybe not Heartbleed or something like that, but definitely something that should actually be checked upon and that cost us close to nothing. Just to mention, pict has some support for conditional situations. So if we look at the parameter file again, so pict image convert.pict. So for example, this other option here, -c, which is, let's call it another knob, can only be used with qcalc2 files. So there is support for conditionals like this. And if we activate it, and let's just run pict on it because it's going to be faster, you're going to see that compression has only been activated when the destination image is a qcalc2. So you can pretty much build on those concepts. So what's next? We want to get Avocado and like the tools that are necessary to make this kind of tooling and techniques available to upstream virtualization development. We are currently doing an experiment in upstream QEMU. This is one of the implementations that we have. Interesting news is that there's been collaboration with the Czech Technical University in Prague, in which another algorithm is being developed specifically for Avocado now, and we're going to let the best solution win. We have found that this is quite a topic that has not been thoroughly used in upstream, so we can probably see as a next step a special interest group or something like that. On our side, on the virtualization team at Red Hat, we really want to leverage this kind of situation to allow individual virtualization developers run a much higher coverage of tests, like using a lot less energy, be it like human-based energy on like writing less tests and using less resources as well. Any questions?
Was the total count of all variants if you did not use pict?
It was, oh, I didn't do that count, but, oh, yeah, it's like 3,800. Yeah, actually, when I use 05, I mean that I want all the unique values, and I have 5 different input types, so it's 389 different variations. That's it is a speed up.
So is which version of Avocado is the pict integration?
So yeah, I briefly mentioned, so we put that out as a proof of concept. It's in a specific pull request. And what's next for us is getting pict itself packaged on Fedora and EPEL, and then pushing proper support on upstream on the next Avocado release. So that's probably going to be 56 or something like that. Yep.
So what's the working mechanism for pict? It's just randomly picked from those variables. How does it know which one is more important to pick?
So there's no difference in importance as long as in the generated test case, so in the list of tests it generates, each input type has at least, it's listed depending on the order that you specify. So for pairwise or order of 2, you're going to find 2 unique values in a test within the test case, right? So the traditional way of doing that is making sure you multiply everything by everything, so you'd have one test with each unique value in all positions. And what pict does, it may have more than once if it's necessary to guarantee that each one is listed at least once, each pair is listed at least once, but that's all it does. Yeah.
Does it generate always the same list, or is it?
It generates always the same list for the same input type. Yeah.
These are deterministic tests. Can those approaches be applied to non-deterministic situations like timing issues or races to detect them?
That's an interesting point. I mean, probably by pairing it with another tool where you can control the deterministic, non-deterministic stuff like timing. Probably yes. So I don't see it being used for that by itself, but in combination with something else, like RR would be an interesting tool to couple it with. Thank you guys very much. If you need, I'll be here for a few minutes, and you can find us online. Thank you very much.